So places where this might be discontinuous would be if we had divide by zero issues. So we want to factor the denominator. I mean, you could factor the numerator too, and I'll do that. Yeah, let's factor out a negative sign. That makes it easier. Because maybe we'll see something that we should talk about. If you cancel them out, you can have a removable discontinuity. So factoring the denominator, we need two numbers that multiply to be negative 3, but add to be negative 2. So how about x minus 3 and x plus 1, because these add up to make negative 2, and they multiply to be negative 3. Now if we finish factoring the numerator, two numbers multiply to be negative 2, but add up to be negative 1. Okay, so this is a good example. You have to take a function as it's stated when you're trying to consider the domain, and same thing with continuity. The way it's stated, if you were to plug in x equals negative 1, you would have a divide by 0 error, even though these cancel out. So what you'll see in Desmos, if you try to get close to negative 1 for this function, is that actually won't have it defined. There'll be a hole there. Okay. So we have to exclude both 3 and both negative 1 because of that removable discontinuity that's happening at x equals negative 1. So our interval would be from negative infinity to negative 1. That's the first value we come to. Stop. Get back on the train after negative 1. Go to 3. Stop. And then go to infinity. These are all the places where it is continuous. Same type of thing with this problem, except now it's a square root. We want to find all the values for x that make it be greater than or equal to 0. So we want to take the inside of the radical and we want to make sure this is greater than or equal to 0. And since it's quadratic, we know its behavior. We know it either looks like this or like this. And since a is positive, it's going to have this sort of shape. We need to make sure it stays above 0. Let's say this is the x and y axis. It needs to be these intervals for where it is above 0 or equal to 0, because we can't take a square root of a negative number without using imaginary numbers. So what we can do is we can find out where the inside of the radical crosses and makes 0. I'm stumbling over my words pretty bad. But we want to find out where the 3x squared minus 9x, where that equals 0, where those crossing points are. And then we can analyze them a little further to make sure that to the left or the right they're greater than or less than. And if you solve this, it's factorable. We get x equals 0 and x equals 3. So we want to check those points on, like, using a number line. Here we can plot x equals 0 here and x equals 3. So it's a quadratic function. I kind of gave it away with the structure of that graph, but what you want to do in calculus is, if you're trying to find out where something's greater than 0 or less than 0, and if the function's getting a little complicated, make a quick little sign chart. Like if you were to plug in a number to the left of 0, since it's continuous, we know it's going to always have the same behavior. Like if you plug in x equals negative 1 into this, then get negative 1 squared is 1. 1 times 3 is 3. 3 minus a negative 9 is going to be 3 plus 9, so it's going to give us 12. It's above 0. And that means, since it's continuous, it's going to be above 0 for all these other places. So where is this thing continuous? It's continuous from negative infinity up to negative 1. And let's put a pin in that because, oh, sorry, whoa, up to 0. Negative 1 was just a test point, right? It crosses at 0. And that means actually we need a bracket because x equals 0 is perfectly fine. Square root of 0 is 0. And now we want to test in between. So like if you test x equals 1 in this function, 3 times 1 is 3, 3 minus 9 makes negative 6, and the square root of negative 6 is imaginary. So nothing in between x equals 0 and x equals 3 will work because we tested a point. And that only applies because it's continuous. Okay? If you don't have a continuous function, if it jumps all over the place, then this doesn't work. If you plug in x equals 4 into the function, something slightly to the right of this other endpoint, we get 4 squared makes 16. 16 times 3 makes 48. And so that's 48 minus 36 gives us 12. So that's going to be square root of 12. That's a positive number. So it's positive to the right of x equals 3. But this is just confirming that intuition that we got from thinking about the graph of this quadratic. 3x squared minus 9x. The a, the leading coefficient, is positive, so we knew that graph would look something like this. And since we found the endpoints, actually, I'm drawing it on the wrong side, but since we found the endpoints, x equals 0 and x equals 3, then we knew that it was going to be positive to the left and to the right because we knew something about the behavior of a quadratic function.